Alright, hello and welcome to the fourth lecture of Chemistry 390, where this lecture is going to be entirely focused on water and soil chemistry. Really what I mean by this is the effects on water post-wildfire that result from soil runoff, as we'll see in a sec. And this is a really important topic, especially in the region of California, because a lot of drinking water is adversely affected because of wildfires, where what I'm showing here in this map, I guess, to the right, is the region of the San Francisco Bay Delta watershed, where millions upon millions of people get drinking water from here, and it's really, really important for agricultural uses as well. And we're going to talk about today some of the chemistry that can result in soil and how it ultimately affects drinking water. Okay, so let's just quickly recap last time. Last time what we talked about was ozone in the troposphere, or smog. So we talked about how smog can form from cars. And then we talked about how cities can be adversely affected in terms of their air quality, where smog, or really what I was talking about in that lecture, was ozone that results from wildfires. And we talked about how different geographies can result in different relative amounts of ozone over different time scales. So recall, like, temperate wildfires produce generally lower ozone but over a longer period of time. And then wildfires in the tropical areas, so I'll say tropical fires, generally produce more ozone because they have more nitrogen content in the plants, leads to more NOx, ultimately allowing more ozone to form. And then these were also over a shorter period of time. I'll just write the ditto signs here. So shorter period of time. And the implications from this are interesting, where wildfires in temperate regions can have a global impact, really depending on wind patterns for air quality and ozone production. So some really, really interesting stuff, also very troubling things that will inevitably become more prevalent in our warming climate as wildfires increase. Okay, so today we're going to be talking about soil chemistry and water chemistry, so it's a good idea to, or rather a good place to start would be to lay a foundation. What is in soil? What is the baseline chemistry there? And how will it change as a result of fire? Okay? So soil is oftentimes broken down into what are called horizons, or just like regions of the soil. And the most important ones for our discussion today will be the organic layer, O, or the O horizon, as it is often referred to, and the A horizon, or the topsoil layer. Okay, so in these layers, predominantly, or the material that predominates in these layers, is organic matter that is ultimately formed from plant decay. So as plants die, some of them are covered into the soil, and these are largely in the form of what are called fulvic acid and humic acid. Humic acid, commonly referred to as simply humus. So I'm not talking about like the Mediterranean crushed up chickpeas. That's hummus with two M's. Humus is a material, organic material in plants, or rather in soil, that results from plants, and it's a source for like insects to get food from and stuff. Okay, and the main difference between fulvic and humic acids is, well, let's talk, I guess, first about their similarities. You'll notice that they are both called acids. So what this acid part in the name is referring to is the presence of CO2H. So this chemical, what we like to call functional group in chemistry, or like a moiety. What this is it gives it acidic character. So think like eating sour candy or eating citrus fruit. So citrus fruits have citric acid in them, giving them that sort of characteristic sour, tart flavor. So in this case, it's not really relevant to think about the flavor of fulvic and humic acids, but really the fact that they behave as an acid sort of just governs some of the chemistry of uh, these top layers of soil that we don't really need to get into, mostly because we would have to delve into acid-base theory and give you a foundation in that. So rather than do that, just know that the presence of acid here is referring to these types of bonds. And what this line here I drew next to the carbon means that there's just other things that it could be bonded to. So it could be bonded to other carbon atoms for to have like a larger chemical structure. And really, it's just the presence of this group, or rather, the presence of multiples of these groups that makes these things relatively acidic, okay? And another big difference here is that humic acid tends to be much larger than fulvic acid. So on the order of like, if you had a molecule of humic acid versus a molecule of fulvic acid, humic acid tends to be, on the order of magnitude of hundreds of times larger. So it's just a bunch of carbon, hydrogens, and oxygens all linked together in this cross-linked, really complicated way, and also includes some of these acid groups here. Okay, so that's like the main difference between the two. And one thing that's important that results from humic acid and fulvic acid is their relative large size makes them rather insoluble in water, in H2O. Okay? So another way to refer to this is that these are relatively hydrophobic. Oops, there's a B. Hydrophobic. So phobic comes from phobia, means fearing. Hydro, water. So this word literally means water fearing. Or they fear water. They don't want to mix with water. So we're going to be using this term a little bit later on throughout this lecture. So just know hydrophobic means that they don't like water. Don't like water. Okay, so they generally are not extracted into water as it like rain were to fall on the soil. Okay, so then another important component of soil is sort of the inorganic stuff, which remember in the world of chemistry, when we say something is inorganic, means we don't really care about carbon and hydrogen bonds, so no CH present. So carbon and hydrogen are not major chemical components of inorganic matter. So what are the major components? Well, in the case of soil, the biggest thing are what is called silicates, or SiO2. So silicates is just like a general way of describing dirt, where dirt is little particles of silicon bonded to oxygen in different ways. And there can also be some aluminum in here as well. So aluminum can take the place of silicon in some of this bonding, but basically this is what is referred to as like the minerals. So minerals is just like naturally occurring silicon, aluminum, calcium, phosphorus, just as they are in like the dirt. So yeah, this is sort of what's meant by the inorganic components in soil. Okay, and in general, silicon or silicates tend to be hydrophilic. hydrophilic. I think there's two L's in that. There might not be. Actually, I think there's just one. I'm going to get rid of one of those. But these are hydrophilic, so this just means they do like water. And what's important for this is they allow water to migrate into soil. So if soil were entirely composed of humic acids and fulvic acids, the water wouldn't really penetrate into the soil. It would sort of beat up on the surface and skirt off the surface. So because of the presence of silicates and aluminosilicates, what happens is the water is able to migrate into the soil and wet the outside of these silicate particles. But the particles themselves are rather heavy and don't necessarily like dissolve into the water, so they stay in place. Rather, the water sort of migrates through it. And this sort of is a nice prelude into what I have on the next slide anyway, so let's just go ahead and jump right in, where water runoff, typically the way it works is when it rains and stuff. So here's just like a little cross section of land and soil. So water will some flow off the surface of soil, but also water is able to migrate into the soil, ultimately just flowing downhill to where a stream will result, and the water will end up there either through groundwater flow or just on surface flow, okay? And it can carry some chemicals with it along the way to add some more chemical components to the water in the stream other than just H2O. We'll talk about what components are naturally leached from soil, and then how the chemical components leached from soil drastically changes as the result of a wildfire, okay? So one thing that results after a wildfire is the soil erosion significantly increases. So this is water runoff after heating soil. So what I have in this figure on the right hand side of the slide here is that what these researchers did is they took soil from specifically the region they got the soil from was from Boulder, Colorado, and they heated it up. So they just took this soil and they heated it, a batch of it to 150, another batch to 250, a third batch to 350, etc. And they just dunked it in water and measured how much of the organic, or rather the carbon and nitrogen content of the soil changed as a result of exposing it to water, okay? So if you look at their control run here, what this means is they didn't heat the soil at all. They took the soil, dunked it in water, then measured how much carbon and nitrogen left the soil, and pretty much none of it. Like all of the carbon and nitrogen stayed the same, okay? And I should mention that they're looking at the organic layer and the mineral layer. So if we look at our graph up here, these researchers are looking at the O and A horizon specifically, okay? And what they see is that as the soil is heated up to higher and higher temperatures, more and more of the carbon and nitrogen content in the soil eventually leave, okay? And I didn't really mention it, that's one thing I forgot here, is that this organic matter from plants contains a lot of carbon in the form of fulvic and humic acids, but also contains proteins from decaying plants or dead plants, essentially. Well, remember, proteins are just chains of amino acids, and amino acids contain nitrogen. That's one of the main chemical components, or rather elemental components of amino acids, is the presence of nitrogen, okay? So an example of an amino acid we gave earlier in the course was glycine. This was like C2H, I think it was H5. I really should know this better by now. The number of times I've written this is too many. But regardless, it's some mixture of carbons, hydrogens, nitrogens, and oxygen. But the important part in the proteins here is nitrogen. So, and of course, because plants are living organisms, they have DNA. So a lot of the DNA that is in plants, so DNA meaning deoxyribonucleic acid. The important thing here is that DNA has a lot of phosphorus, if I can spell. And this phosphorus is just a component of DNA, but I guess all I'm trying to get at here is that a lot of the organic matter in the O and A horizon in soil is coming from, decaying living organisms, plants, and there's also bacteria and stuff in the soil that are fixating nitrogen to allow new plants to grow. That's sort of the natural cycle there. But there's sort of, when I'm saying organic matter in the soil, think like the elements related to life. So carbon, hydrogen, oxygen, nitrogen, phosphorus are sort of the 5 main big ones. And we'll see all of these really throughout this lecture for what changes to water runoff, or what chemical changes result in the water as a result of soil changes from wildfires, okay? So all of that was just explaining why are they looking at nitrogen percentage in the soil, because nitrogen's there from proteins, from decaying plants, okay? But anyway, the main finding, the main interesting thing was that by simply heating up soil, the amount of carbon and nitrogen that can then leave the soil significantly increases, where in the limit of 550 degrees Celsius, so this is also, don't know if I mentioned that, heating temperature in degrees Celsius, in the limit of heating it up to 550 degrees Celsius, pretty much all of the carbon, all of the nitrogen, for some reason that we'll explain, is converted into a water-soluble form and is able to be extracted into the water, okay? So I guess this leads to an interesting thing that to explain here. Why does this happen, okay? So why it happens is because a lot of the humus and just organic matter, so I'll say humus and organic matter, largely gets converted into water-soluble forms. Where I mentioned earlier that humic acid and fulvic acid tend to be kind of large molecules that contribute to them not wanting to mix with water. The presence of heat causes them to sort of break down and form other components that are more water soluble. And what those water soluble forms of carbon and nitrogen are shown here in this plot. So this is a similar study on different soils, really, but what these researchers did is they looked at soils from, I don't remember the acronyms, what they were, but it's not important for our discussion. All that matters is that these are 2 soils. So this, and soils from Colorado again, so we're still in Colorado. And this was from an area that was fire afflicted in the past. So this is from an area that had recently experienced a wildfire, and recently meaning like years ago, wasn't like, the day before. And this other sample was not fire afflicted. So they were just comparing soil differences in terms of longevity after a wildfire, like 5 years after a wildfire. Is the soil still drastically different? But regardless, what they saw for both of these samples, these soil samples, after they heated them up, was a significant increase in some of the organic matter that was extracted from the soil, okay? So what we have here, there's a lot obviously, so I'll do my best to explain this in as simple terms as possible. So they measured a lot of black carbon increase. So you see black carbon is the first column here. So unheated in both is pretty low. And then as the black carbon increased, so I guess I'll use black for black carbon. So here, black carbon. As the soil was heated, the black carbon increases. Okay? Generally. So what these researchers were referring to when they say black carbon was things like polycyclic aromatic hydrocarbons, or PAHs. So think like naphthalene, like C8H10, I believe. Or, excuse me, I got those backwards, C10H8 rather, but just forms of carbon and hydrogen that sort of result when organic matter is heated up in a presence where there isn't a lot of oxygen. So normally when you heat up organic matter, it's going to want to form CO2. That's like the most stable thing that can form. But when there's not enough oxygen present, so somewhere like in the soil where oxygen is coming from the air, so it might get depleted as the fire burns in the soil, the organic matter can be converted into black carbon, so C10H8, and it can be converted also into black nitrogen, which is similar to polycyclic aromatic hydrogens, but it's stuff like this with the nitrogen instead. So an example would be, I guess the simplest example would be something like pyridine. So pyridine is really one of the most simple examples of a black nitrogen molecule, where it's similar to polycyclic aromatic hydrocarbons. It's just some of the carbons are replaced with nitrogens, okay? Where the chemical formula of something like pyridine would be C5H5N. And obviously there's going to be a wide variety of like black carbon and black nitrogen, which is why the authors or the researchers here did not ascribe it to a specific single chemical. But regardless, that's just sort of the structures I'm referring to here. And then there are polyphenols, which also increase. I guess let's finish up on black nitrogen here. You can see black nitrogen in red, so let's get red for black nitrogen. So black nitrogen increases the most by a long shot here, where black nitrogen levels just really skyrocket as a result of heating the soil. And then the last one I'll touch on here is that the polyphenols. So the polyphenols is, again, similar to polycyclic aromatic hydrocarbons in terms of their structure, except they have like OH, oxygen and hydrogen in small amounts added in. So a phenol, so the molecule phenol, I'll write that over here. This is, I guess I don't need the parentheses. This is C6H6O. So it's just carbons and hydrogens with a really small amount of oxygens present as well. So the word poly just means that it's a bunch of these bonded together. So this one's bonded to a C6H6O, then that will be bonded to a C6H6O, so on and so forth, forming this larger extended structure, okay? So what's important to note here is that the amount of black carbon doesn't go up a whole bunch because these molecules are actually fairly hydrophobic, meaning they don't really want to mix with water, but the presence of nitrogen and oxygen in the black nitrogen and polyphenols makes these relatively hydrophilic. So I should say the presence of O and N, the oxygen and nitrogen, make them relatively hydrophilic. And ultimately, the important point of what's happening here is a lot of the humus, a lot of the organic matter present as humus, which remember is generally hydrophobic, is being converted as you heat it up in a wildfire. So as you apply heat, which, by the way, the heats they are applying here are fairly representative of what would be present in the soil in a wildfire. So the wildfire itself might be burning at like 1,000 degrees Celsius, so very, very hot. But just, 5 centimeters into the soil, into the O and A horizons here, these silicates tend to be very, very insulating. So even just like a couple centimeters deep into the soil, the temperature falls off really greatly. So it might be somewhere in the range of 350 degrees Celsius instead of 1,000. But regardless, the temperatures being investigated here are intentional because they represent wildfire temperatures a couple centimeters down into the soil. Okay, so regardless, this humus that is very hydrophobic is being heated up during the wildfire event and being converted into water-soluble forms or hydrophilic forms of this of the organic matter. So it's being converted into black nitrogen, polyphenols, things that are going to be much more soluble in water relative to humus. And this increases a lot of nitrogen and carbon content. So what is often called stuff like dissolved organic carbon or dissolved organic nitrogen. These are often abbreviated as DOC or DON in the realm of water treatment and water quality assessment. These metrics are going to increase significantly as a result of wildfire burning, okay? And in addition to that, on top of all this, soil erosion increases as well. So not only is the humus in soil being converted into water-soluble forms, what ends up happening is during a rain event after the wildfire, a lot of the soil itself gets swept away with the water into the groundwater or stream or wherever its end destination is, okay? So in addition to all of this, the soil erosion increases significantly. And admittedly, the chemical reasons for the increase in soil erosion aren't really well defined, but basically the general consensus of what happens leading to what is called the tin roof effect is picture like a hill, and then when you have like your layers of soil in this hill. Hopefully my drawing is making sense here. Here, let's try this. Let's skip the layers. Let's draw like a tree, so you know that this is land and this is like a hill where the leading down from the tree. And what a fire does. So when this tree is on fire, here, let's draw the fire in orange. Give me a sec. Okay, this is my feeble attempt to draw a tree on fire, but let's just label it true. 2. Tree on fire. So what happens here is a hydrophobic layer parallel to the ground forms. So this is a hydrophobic layer. And the best idea, the best hypothesis for why this forms is because some of the organic matter present in the A and O horizons in the soil, those first few centimeters, are relatively volatile, so they vaporize and move away from the fire down a temperature gradient. So the temperature will be relatively high at the surface of the fire, and there's like a temperature gradient where temperature decreases as you move into the soil. And as things tend to move from high to low temperature, these volatile organics and the O and A horizon of the soil move down into deeper regions on the soil. And remember, these organic things are generally hydrophobic, and they sort of create this hydrophobic layer deeper into the soil. I'm not going to test you on any of that, mostly because it isn't really well understood by experts themselves. So if experts don't really know what's going on, I can expect not experts to know what's going on, okay? But regardless, the end effect of a wildfire is that a hydrophobic layer parallel to the ground forms and ultimately results in what's called the tin roof effect, where the region here above the hydrophobic layer, this is relatively dry and wettable, because soil in its natural state is going to be somewhat wet, somewhat hydrated, because remember, the silicates here present in dirt are generally hydrophilic. They will mix with water, or rather water will easily wet the surface of those. So a fire, partially what it does is the wildfire will vaporize some of the water in the soil. So it vaporizes H2O in soil, leaving behind on the top surface of the soil a rather dry and wettable layer, okay? So the reason this results in what's called the tin roof effect is, imagine you have a tin roof like I got from this installation video from Home Depot, and imagine there's a bunch of plant matter on the roof. So I'll just draw like some squigglies. Think of this as like leaves, some stems, pine needles, whatever. So what happens when you introduce water from, like, let's say a rain event here, so these are little water droplets, what's going to happen is all of this will flow off of the tin roof surface and onto the ground below. So now we have, oops, I wanted to change that to green. So now we have like a bunch of plant matter that falls off the tin roof. So that's exactly the same concept of what's happening here in the soil, is that this dry, wettable layer, as soon as water is reintroduced, so as rain returns, let's say, post-wildfire, the top layer of soil is washed away, which results in more what is called sediment washing into the watershed and ultimately like the stream where the water ends up. Okay, so just to reiterate all of this, fire vaporizes a lot of the water in the first top layers of the soil. This leaves it dry and relatively wettable. Normally what would happen is when water hits the soil, it penetrates and goes all the way down, ending up in groundwater. But the presence of the tin roof effect, what that results in is basically this impermeable layer. I guess it would be higher up than this. It wouldn't be that deep. It wouldn't be like down to the bedrock, but it would be like, here. So it results in this, what I'm drawing in orange, a sort of hydrophobic layer parallel to the ground's surface. And as a result, the water no longer penetrates all the way into the soil, So as soon as it hits this hydrophobic layer, it goes down that and sort of carries a lot of this top layer of soil with it, okay? So this tin roof effect results in a lot more sediment washing into the stream, where the water will eventually end up, allowing plenty of time for these water extractable compounds that form during the fire to migrate into the water, okay? So I guess the point of why I'm bringing all this up is that what these researchers showed was that a higher amount of organic matter was able to be extracted into the water as a result of the wildfire. But that doesn't occur on an instant time scale, right? So if we were to have normal water runoff with this same wildfire or heated soil, not all of this organic matter would be extracted into the water because there wouldn't be enough time for it to do so. So I guess the importance of this, let's put it in words. So this allows more time for water extractable organic matter to enter the water. Okay? So ultimately, the end result of the tin roof effect is a lot more sediment in a stream, in a natural waterway, which will result in a higher amount of dissolved carbon, dissolved nitrogen, dissolved phosphorus, etc. to go into the water, okay? So ultimately, the main result from this soil erosion and these changes in soil chemistry result in the water needing to be treated more than usual because now there's more stuff in the water, okay? So the second part of this lecture is going to be all about, how do we treat water and how do these changes that result from wildfires require, or what sort of changes need to be made to water treatment processes to get all this stuff out, okay? Because ultimately what we do when we treat water is we convert it into some form that is drinkable and usable, okay? So we take our water source, so this is runoff from mountains, groundwater, waters from aquifers, etc. Depends on the region you are in. This is introduced to what are called coagulation chemicals. So what coagulation chemicals are, some examples, is stuff like iron chloride is a common one. An even more common one is what's called alum or aluminum sulfate. So aluminum sulfate. And this could also be like potassium aluminum sulfate. That would be a 2 there. But regardless, what these do is they cause small particles to clump up. So the main thing that coagulants do is they cause coagulation. They cause, or they make, small particles clump together. So you can imagine that a lot of the organic matter that is, or rather a lot of the sediments that is washed into a natural waterway, some of it might be composed of very, very teeny tiny particles that are able to be suspended in the water and don't naturally settle out if you allow it to just sit, okay? So what this coagulation does is it allows for these small particles that clump together into bigger particles, ultimately allowing them to settle out if you let the water sit for long enough, okay? And that's really what alum is. Alum has this really open, porous crystal structure that allows little tiny things to get stuck into it making it heavier and settle out of water, okay? But anyway, let's keep going to flocculation. So flocculation is really a secondary step that needs to be done in order for coagulation to work properly. Really, in terms, in the simplest terms possible, what this is gentle mixing after the coagulant is introduced. So this allows for the clumps that are starting to form at the beginning of coagulation to mix together and form even bigger clumps, okay? So the important step or the important purpose of flocculation is this allows for larger clumps to form, in essence. Obviously, it's going to be a little bit more complicated than that, but for the purpose of this course, this is enough, okay? And then this leads to sedimentation, which you can see in this picture here. This is just letting the water sit and letting those flocculants and coagulants, those things that caused all that clumping, all of that settles out from gravity, and the top layer of this sedimentation tank is what is extracted, because now that is water with relatively low amounts of like dissolved solids in it. So I guess we can put some text here. So I'll say clumps settle out. So they just fall to the bottom, take off the top layer. That is now water with relatively low clumps in it, let's say, okay? And then it is filtered. So this is often just passed through what's called an activated carbon filter, which is something that you might have in like a Brita filter at home. That's just activated carbon. It's just porous carbon that's similar to alum, let's say. As things migrate through it, they get stuck in there, okay? So this is just an extra step to filter out some of the smaller particles that might be still left behind. And at this point, what you have is water with, if anything, really, really, really tiny things that could not have been removed from an activated carbon filter, okay? Which leads to this last step, disinfection. So this is adding some chemical oxidant in the form of often chlorine, or ammonia is sometimes used, or ozone could be used, bleach could be used. So all of these things, well, not ammonia, the chemical reactivity of ammonia is slightly different, but bleach, so sodium hypochlorite, so this is bleach. So chlorine, ozone, and bleach all have similar chemical reactivity, where what they do is they kill living things. So the important step of, or the important purpose of disinfection with some chemical oxidant is to kill microorganisms. Those could be bacteria, this could be viruses, could be a lot of things. But it's killing microorganisms and also removing any remaining organic matter that didn't quite get washed away or removed from the coagulation and flocculation steps, okay? So the idea here is you're taking the organic content in the organic matter, so that's the carbon. What the heck? Why is my pen doing this? So it's taking the carbon and converting it to CO2. You're oxidizing it, okay? And there might be some additional steps depending on the source water used or what contaminants are present here, but this is in general the same sort of flow that is used at any water treatment facility to provide drinkable water to people in the surrounding area, okay? So what we're going to talk about now is how wildfires sort of disrupt this process. What do they do? So one step that is an important impact of wildfires, so now we're talking about wildfires effects. One thing that they do is that a higher amount of dissolved organic matter, or DOM, so this is dissolved organic matter. I'll write it really small. Dissolved organic matter. What this results in, so higher dissolved organic matter in water, which remember results from wildfires, causes a lower coagulation efficiency. Coagulation efficiency. So remember, the coagulation was this first step where most commonly something like alum is added to the water to cause things to clump together. With more organic matter in the water, the clumping efficiency, or how well the coagulant makes things clump together, goes down. So as a result, more coagulants need to be added. More coagulants we'll say needed, which is not good, especially in rural communities where they don't have infinite money, or they don't have a large amount of money to spend on additional water treatment steps. So more coagulants needed results in ultimately higher costs for, that's supposed to be a dollar sign, for water treatment, which in some cases from post-wildfire, some water treatment facilities just have to shut down because they cannot produce drinkable, usable water with the resources and the funding they have. So it can be really, really devastating for smaller rural communities. Okay, so let's just look at an example here of, if I can find my mouse, there we go, of the effects here from dissolved organic matter, the impact it has on coagulation. And I don't have a citation here, but it's the same paper as here. So the same people who were heating up soil and measuring the carbon and nitrogen content that left it, they were also looking at, okay, there's a bunch of carbon and nitrogen in the water now. How does that impact water treatment efficiency? Okay, so what they're showing here, so this is dissolved organic carbon, dissolved organic matter. So I should have thought more about making this slide. This is an annoying thing with water treatment science, is that there's so many acronyms. But hopefully I don't lose you here. So this is dissolved organic matter, which can include more things than just organic carbon, just because organic matter can also include other elements. And then this is specifically focusing on the dissolved organic carbon, so the carbon content of that dissolved organic matter, okay? But regardless, what you're seeing here is that this is sort of like a base flow snow melt. So this is like when snow melts off a mountain, that's often collected for drinking water uses. And this is post rainstorm. I should also mention post wildfire as well. And this is again in Colorado, where they used initially a higher, this is just showing that there is more DOC post wildfire. Expected, because more soil erosion. The wildfires also convert a lot of the organic matter in soil to be water soluble. So as a result, before wildfire, less dissolved organic carbon in the water. After wildfire, more dissolved organic carbon. Totally unexpected result, okay? And because of the higher dissolved organic carbon, what these researchers did is they used a higher alum dose, which again is our coagulant. So they were just following procedures that a wastewater treatment facility would use. And so they used a higher dose of alum compared to the pre-wildfire soil sample. And as a result, the treated water, so normally there's relatively low dissolved organic carbon, which is what you want. That's why you're adding this coagulant. You're adding it to make these small suspended particles of carbon clump together and settle out as sediment. But in the case of the post-wildfire soil samples, what happens is even after a higher alum dose is used, so even after the higher coagulant dose, unsafe levels of dissolved organic carbon persisted. Now, that's not good. So even though they used a higher coagulant dose, it still wasn't good enough. So they have to, if this were in the real world, go back and add even more coagulant. And if you imagine this on a citywide scale, producing drinking water for millions of people, that's going to result in a really, really high cost. Alum isn't necessarily an expensive chemical, but on these large scales, having to double or triple the amount of coagulant that you use in this wastewater treatment really results in a prohibitive cost in some cases, okay? And then we don't really need to talk about this. So what this is just an absorbance measurement. We don't need to talk about it. Just basically, okay, let's just, for the sake of simplicity, I don't want to have to explain UV visible spectrophotometry, so we're going to ignore that one. And the takeaway here is that more organic carbon persisted even after using coagulant, which is not good, okay? And then additionally, on top of this, another harmful result from this increased levels of organic matter in water is the presence of what's called disinfection byproducts in water treatment, where remember, this disinfection step in the water treatment adds some sort of chemical oxidants. So this disinfection byproducts, what these are byproducts that result from disinfection, which is maybe in the name. Let me make this a little bit more specific. Byproducts from organic matter reacting with the disinfectant, most commonly chlorine. So I'll just use that as our example for this slide, okay? So some of these byproducts result from the fact that you're mixing carbon and hydrogen, because remember, organic matter is usually just some form of carbon, hydrogen, oxygen, and it can be some other elements, but what's important here is the carbon and the hydrogen. If you take these and mix them with a chemical oxidant like Cl2, what you can form are what are called trihalomethanes. Or in the case if you're using chlorine as your chemical oxidant, you would form chloroform. So trihalo, halo just meaning halogen. So chlorine is a type of halogen. That is the chemical elemental family it falls under. Other examples would be fluorine, bromine, iodine. Those are your halogens there, so it's really just 4. Technically, there is also astatine, but this is so radioactive that it's not actually stable, so we can just stop at iodine. Whatever, that information isn't very important. All it means is trihalo, so one of these elements, there's 3 of them, and then methanes is just referring to 1 carbon. So here, this one is called chloroform, which if ingested, so you might know chloroform as being a very old anesthetic to make people pass out before surgery. So that's because you inhale the chloroform. It has a very low or very high vapor pressure, so it basically, if you have a rag soaked in chloroform and you start breathing from it as if you were covering your mouth with it, it prevents you from breathing in oxygen, ultimately resulting in you passing out. So we're talking now if you were to drink water contaminated with chloroform, the end result here is that this is carcinogenic, which results in, obviously, by the name, cancer. So not good for people to be exposed to. Okay, so the end result here, where am I going with all this? Let's just do like a little flow of thought. So wildfires result in more dissolved organic carbon in water because, one, it converts them to water-soluble forms. It converts the humic acids and fulvic acids in water or in soil to water-soluble forms. And then two, it also just increases soil erosion. So just the amount of soil in water increases. Um, um, you might not think this is a big deal, but what this results in is then more what is called total trihalomethanes. So trihalomethanes is abbreviated THM, so even more acronyms, our favorite. And then for water treatment facilities, they quantify the total trihalomethane content. So that's what this second T is for. So it's total trihalomethanes. So there's more total trihalomethanes in water. And I should also mention that the dissolved organic nitrogen can also form disinfection byproducts. So quickly we can go over what those are. Okay, so I made some room here. So we can also talk about the fact that organic nitrogen and also like black nitrogen that was discussed previously on the other slide. So I guess I'll put that in parentheses because that applies here as well. So black nitrogen can be lumped into organic nitrogen, but specifically in our lecture, we talked about black nitrogen, so we can talk about it here as well. So if this reacts with Cl2, it can form what are called halo. So again, halo for halogen. Chlorine is the halogen here. Haloacetyl or acetonitrile, nitriles, which is abbreviated HAN. So haloacetonitriles, HAN. And these are okay, well, so acetonitrile is basically C2H3N. That's like the chemical formula for acetonitrile. And then chlorine here, what this would do is it would displace one of the hydrogens, like so. And it could be like it could be just like 3 chlorine, so C2Cl3N. But it's basically some amount of halogen chlorine on this base acetonitrile structure. And this is, again, another toxic chemical to ingest, where specifically these are also, or they can be, carcinogenic. And they can also lead to gastrointestinal issues, which we're going to cover a little bit more of this with toxicology of wildfire byproducts. But in general, we can just preview it here. But regardless, the wildfires increase dissolved organic carbon and dissolved organic nitrogen in water. This leads to more total trihalomethanes and then more haloacetonitriles, which ultimately the end result isn't that like people are going to be drinking more of this. It's just that more water treatment is therefore required to get rid of these. Which ultimately just leads to more cost associated with treating water, which, like I said, could be very devastating for smaller rural municipalities. And specifically, the way you remove total trihalomethanes and haloacetonitriles is just by adding another coagulant step to cause those to coagulate and settle out. Okay, so I guess the end result here, the end takeaway is that wildfires negatively impact water chemistry and the treatment process for making safe and healthy drinking water. And the way they do that is by chemically changing the soil and also increasing soil erosion as a result of the wildfire. Okay, so rather than ending on this sort of sad note of like, oh wow, wildfires are not good. I mean, there are ways to prevent the increased soil erosion. There should be a D here. After a wildfire. And some common ways of doing this is with what's called straw mulching or mulching. So what this does is you're just essentially adding straw or like hay to surface of soil after a wildfire occurs. And what this does is it helps to prevent a lot of the soil erosion from occurring, where this sort of acts as like a repelling layer, or this acts as like a repelling layer that prevents rainwater, so I'll just say H2O, from washing away the soil. And some other methods are also used, like there's like seeding, which basically the idea is you're planting seeds for plants to grow. So you're ultimately increasing plant coverage to ultimately achieve the same effect as straw mulching, where some of the water then will be sort of repelled by the surface plants, not seeped into the soil. And remember, because of that hydrophobic layer that forms and the tin roof effect, preventing the water from getting into this top layer of soil will prevent a lot of the soil erosion. So those are some common strategies to prevent soil erosion after a wildfire. So it's not like we're doomed, it's just that there will need to be more remediation efforts like this after a wildfire. And then one researcher that proposed the solution I thought was relatively interesting is they said a reliable way to prevent soil erosion is just have more prescribed burns. I'm not certain if this is something that is resulting from wildfires becoming more prevalent. I don't know if there is more prescribed burning occurring. But the idea here is that you sort of I guess prevent major amounts of soil erosion after a wildfire, where the idea here is that if you have smaller prescribed burns regularly, so these smaller prescribed burns ultimately, if they are smaller, result in lower temperatures, which result in less chemical change of the soil and less erosion as a result. And then by having these prescribed burns, you are also reducing the amount of plant matter present. So if a wildfire were to occur, were to break out, it would be less severe and ultimately prevent a lot of this soil erosion from occurring. It was an interesting idea. I thought I'd include it here, but I think the predominant sort of method that people seem to be promoting is straw mulching post-wildfire, okay? So that's pretty much everything I wanted to cover in this lecture. We're going to talk a little bit more about the toxicology of some of this stuff. If you thought it was a little bit disappointing that I just said these were carcinogenic and moved on, we'll talk about that more in our toxicology lecture. But just looking forward, our next lecture will be focused all on the vegetation effects, or the impact of the type of vegetation on wildfire aftermath. And then we'll move into our toxicology lecture. I should mention also that exam 1 will be after the vegetation lecture. Then we'll do our toxicology lecture and then talk about some firefighting chemistry. So how does a flame, what sort of chemical characteristics are at play when extinguishing a flame? And yeah, so I think that's pretty much everything I wanted to cover. So please let me know if there's any questions. I realize there was a lot in this lecture, a lot of acronyms. And yeah, I will see you in the next lecture.